Greetings, logic students. Let's think about logical possibility and truth. One way philosophers think of this is that the truth conditions of sentences are made up of the ways the world might be if the proposition were true, and the way the world might be if the proposition were false. The truth table is said to be a representation of all the possible ways the worlds might be in terms of that proposition. This interpretation of the truth table was independently developed by the American philosopher Charles Sanders Peirce and the Austrian philosopher Ludwig Wittgenstein in the early 20th century. Wittgenstein wanted to think about how we think about the world, right? That's kind of fun, to think about how we think about the world. And one claim he made is that what we mean by the world is all that is the case, all the sort of true things about the world that we could say about it. So in thinking about the world, we can think about the claims that are true of the world, and we can think about the claims that are false of the world, and in that way, he thought, see more clearly how the world is. There are ways the world might be if the propositions were true, and ways the world might be if the propositions were false. And truth tables display these truth conditions through showing the truth values of the compound propositions, which are then determined by the truth values of the simple propositions that make up those components. Now, in calculating truth values, in the last chapter we studied, we determined the truth value of a compound proposition given certain assigned truth values. But with a truth table, we can consider every logical possibility, and with each line of the truth table representing one of these possibilities, one of these possible worlds. So think about logical possibilities and truth. Consider the statement that it's cold outside today. Well, it's either going to be true that it's cold outside today or false. But then we could complicate matters by considering two statements. It's cold outside today and it is windy. So it is cold outside today could be true or false, and it is windy could be true or false. It could be that it's cold and it's windy, or it's cold and it's not windy, or it's not cold and it's windy, or it's not cold and it's not windy. Which is to say, our two statements could both be true, while one can be true while the other is false, or both can be false. So for one proposition, we would have two assignments of truth value, right? It is cold. It is true that it is cold, or it is false that it is cold. If we had two propositions, we would then have four assignments. And there's a pattern to it. 2 to the n power, where n equals the number of statements we're joining together. So if we had 3 propositions, we would then have 8 possible ways the world could be, and so forth, right? 1 proposition, 2 rows, 2 propositions, 4 rows, 3 propositions, 8 rows, or worlds. 4 propositions, 16, and we would go on, right? And the number of rows would grow, as they say, exponentially. So let's think about what truth tables do. And let's see if we can make sense of this definition. Truth tables graphically display the truth conditions of truth functional statements. First of all, what are truth functional statements? Remember that these are compound statements whose truth value is a function of the truth value of their components. These compound statements are built up out of simple statements by joining them with our connectives, and, or, if then, if and only if, and not. Which leads us to the other element in our definition of a truth table. What are the truth conditions of a compound statement? Well, those are the conditions under which the compound statement as a whole is true or false. So, for example, P and Q is false whenever either one or both of its conjuncts is false. Our truth table definitions of the connectives laid out these truth conditions for our 5 major kinds of compound statements in SL, the language we're learning. Some, again, think of this in terms of possible worlds, which is fun to do. The truth conditions of a statement lays out the way the world might be in which the statement is true, and the ways the world might be in which the statement is false. And a truth table can be said to give us a graphic representation of sets of possible worlds, or more simply and prosaically, combinations of truth values. Now, what does it mean to graphically display the truth conditions of truth functional statements? It means to simply set out in a graphic array, usually in table form, the truth conditions. This is simply the truth tables for the operators we have learned. For example, we graphically display the truth conditions of our 5 operators in the following way, and hopefully you have all this memorized by now. P and Q, or not P, or P and Q, or if P then Q, and P if and only if Q. And there we've graphically displayed the truth conditions. So with all that in mind, we get down to practicalities. We need to learn how to construct a truth table. So, say on an exam, what if I gave you the following statement and asked you to analyze it with a truth table? If they listen to the logos, then either they open their minds to the truth or they listen to the logos. Now I give a dictionary, and notice I've got the cap letters for how I'm going to translate it here, but since I'm going to also put it into universal form, I do the cap letter and then I put the variable. And I do the next cap letter and I do the variable. And I do that as a sort of bookkeeping method so I can keep track of my P's and Q's. Right? So I would translate, if they listen to the logos, then either they open their minds to the truth or they listen, right? If L, then O or L. And then I put it into universal form, which would be P, then Q, then P. Or actually it'd be or P, wouldn't it? Let me go up to the board, erase that, and put that in. All right. Now remember, the idea of a truth table is to represent all possible worlds with every possible combination of truth values. We can use the formula 2n, where n is the number of propositions. So if there are 2 propositions, we'd have 2 times 2 equals 4 lines. If we had 3 propositions, 2 times 2 times 2 equals 8. 4 would be 16, and so forth. Here we have P and Q, only 2. So that's 2 to the second power equals 4. So we need a 4-line truth table. Now during a normal semester, we would just be writing this all out by hand, right? You'd do a P and a Q and do a guide column like in the book, and then write out the formula and so on. But we're online, and actually this has forced me to learn an easy way to generate a truth table in Word, right? Using the table function, which I'm going to show you right now it's actually quicker than writing it out, though I kind of like the sort of almost meditative way of pen and paper method. But this is cool because when you take the exam, you can use this to generate the truth tables, and you won't have to take pictures of your exam and send it to me or anything like that. So hold on a second, because I need to show you this up here so you can see what I'm doing, right? So we have P, then Q or P. Now I'm going to take this and copy it and put it here. And since we have 2 variables, we're going to need what's called a guide column, and that'll be P and Q. We're going to have all the truth values of P and Q. And when you do this, you want to be careful to put a space in between everything, because everywhere you put a space, we're going to get a different column in our truth table. You then want to highlight it. And then you want to go to Insert, Table, Convert Text to Table. And here, it says Separate Text At, and you want to just put in a space. Just hit your space bar once and hit OK. And notice what happened, right? I ended up with a handy-dandy separation. There's my P, my Q, and then there's each separate element that I'm going to need to evaluate. Now at this point, let me move this up, we're going to need to have 4 lines, remember, 4 possible worlds. So if you put the cursor here and just hit Tab, 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 you have 4 rows. Now to make sure we have every possible combination of truth and false, we use a little algorithm, a little procedure to make sure we get it all straight. So in this column, this whole thing is the guide column right here. We alternate, go ahead and turn your caps lock on. True, false, true, false. And then in the next one over, we double it. Okay, so we've got every possible combination of true and false here. And now I'm going to assign the truth values. If you were doing it by hand at this point, you'd write down true, true, false, false, true, false, true, false, true, true, false, false under them. But here's something kind of nice. We go copy, then you click in this space, left click your mouse, and right here where it says overwrite cells, it'll just put it in. Then you can go over here, get overwrite cells, and add that in. And now we put in the Q's. So we copy, then we assign the Q values. Right? Okay. And at this point, I just like to, I don't know why, I just like to bold those because I think it looks nicer. Now remember, you work from innermost out. This is just like we did before in the last chapter, but now we're going to do it 4 times. And we want to indicate our major operator. And an easy way to indicate the major operator is just to highlight it. That's the last one we'll calculate, right? So at this point, we need to do what's in parentheses, Q or P. True or true is true. False or true is true. True or false is true. And false or false is false. And now I'm done with these. So I'm going to go up here, hit this, and mark them out so I don't get confused and try to use them again. Okay? And now I calculate the final element, which would be true, then true is true. True, then true is true. False, then true is true. And false, then false is true. So I'm done with these. And I mark them out. And I'm done with these. And I mark them out. And I'm left with this as my final result. It's come out all true under the major operator. Now what you'll learn in just a few minutes is this is what is called a tautology. And any proposition of this form is a tautology, and so this instance of that universal form is a tautology as well. Now, using this method of generating truth tables, it's important you pay attention to the spaces so that you create a different column to assign truth values. And with negations, what you want to make sure is you go tilde space, tilde space, so that you'll have a separate line. And at this point, I put my P and put my P and Q for my guide column. And let's see if I did it right. We go there, insert, table, convert text to table. Make sure you just have the space there. And there we go. It worked. And then tab, 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 because I have 4 possible worlds here. I go ahead and assign my guide column truth values. Right. Go ahead and put my caps lock on. True, false, true, false, true, true, false, false. I assign my truth values. There's the P. There's another P over here. Then the Q. Then for the settings. Now you always do the negations first. That's just a handy rule to have so that you get everything clear. We got the negation of P here, so that's easy. True becomes false. True becomes false. False becomes true. False becomes true. And I'm through with those guys, so I mark them out. Then I've got a not Q here, so I want to do that as well. True becomes false. False becomes true. True becomes false. False becomes true. I'm done with those guys. Okay. And now I'll calculate what's in the parentheses first, like we've learned to do. So false then true is true. True then true is true. False then false is true. And true then false is false. Whoop, false. And I forgot to indicate my major operator, so I'm going to go ahead and do that. All right. So I'm done with these guys. And I'm done with these guys. And now I calculate the final value. False then true is true. False then true is true. True then true is true. True then false is false. So that shows, for this expression, I come out with a mixture of trues and falses, right? What you'll learn is called a contingency. So again, you want to remember about the spaces and so on when you do this. Now, tautology is a proposition which has a form such that it is necessarily true. This means that it could not possibly be false. It is true under any possible circumstances or in any possible world. So when we analyze the proposition with a truth table, it will always come out as true under the major operator. So consider this statement. Given that both, if he's a Jedi, then he is Force sensitive, and he is a Jedi, then he is Force sensitive. So there I have my dictionary, and as a bookkeeping notation, I put my variables, and that turns into if J then F and J then F, which becomes P then Q and P then Q. And I used my method to generate the truth table, and I've already filled in the truth values, but I'll go ahead and, so what I need to do now is assign these truth values. So wherever there's a P, I need that. There's a P there, so I put them in. And then my Q's. So there's a Q there, so I write those in. There's a Q there, and I write those in. And then I proceed from the innermost parentheses to the next set of parentheses, and we have our major operator there, which is where we'll end up. Okay, so we start with P then Q. True then true is, let me put my caps lock on, true. Whoop, I turned it off. All right, caps lock. True. And true then false is false. False then true is true. False then false is true. And I'm done with these guys. And I'm done with these guys. And so now I move to my next outward parentheses grouping. True and true is true. False and true is false. True and false is false. And true and false is false. I'm done with these truth values. Boom. Mark them out. And now I'm set up to calculate the major operator. True then true is true. False then false is true. False then true is true. And false then false is true. And I highlight that to indicate it's the result. And let's look at the dictionary again. Look at the definition again. A tautology is a proposition which has a form such that it is necessarily true. This means it could not possibly be false. It is true under any possible circumstances or in any possible world. Here's world 1, here's world 2, here's world 3, and here's world 4. When we analyze the proposition with a truth table, it will always come out as true under the major operator. So here we can see that this is a tautology. A contradiction is a proposition which has a form such that it is necessarily false. This means that it could not possibly be true. It is false under any possible circumstance or in any possible world. When we analyze the proposition with a truth table, it will always come out as false under the major operator. So if someone said, for whatever reason, perhaps they're from Bizarro World, either I'm in St. Pete or I'm in Florida if and only if I am both not in Florida and not in St. Pete, I would give my dictionary, I would translate that, right? S or F, if and only if, not F and not S. Right? I am both not in Florida and not in St. Pete. And remember the spaces with the tildes when you generate the truth table in Word. If you don't put a space after that, it's not going to come out right. So there we put it in universal form with our spaces after the tilde. We generate the table. We put in true, false, true, false, true, true, false, false. And you always do it like that. The one to the right, you alternate. The next one over, you double. And then if we had more lines, we'd double it again. And we'll see how to do that in a minute. All right, now we assign our P's and Q's. So there we go. That's assigned, and there's another P there. So I assign that. And now I do the Q's. There we go. Then I always do the negations. That's our algorithm. So not true is false. Not true is false. Not false is true. Not false is true. And then over here we have not true is false. Not false is true. Not true is false. Not false is true. And we're done with those. So we mark them out. Whoops. And we're done with those. And we mark them out. And now we're ready to do this whole expression. False and false is false. False and true is false. True and false is false. And true is true. And now we can do this expression over here. But first, we want to mark out what we've already used. So let's mark that out so we don't get mixed up when we look at our table. This is called an algorithm, remember what we're doing here. So if you follow the rules exactly, you won't go wrong. It's like a machine procedure, as they're sometimes called, a machine decision procedure. Anyway, true or true is true. True or false is true. False or true is true. False or true is true. Ooh, look, I made a mistake. Do you ever make mistakes? I make mistakes. Take a second and see if you can see where I made a mistake. Just look at it for a second. Right? I made a mistake. And it would have totally screwed me up if I was doing this on an exam. So take a second and look at it. I'll count to 10 and see if you spot my error. Okay. Notice here I said you have to alternate. True, false, true. So that should be false. So I'm going to have to go back. I'm going to have to wipe all this out. What a drag. All right. Here we go. Where's my delete key? Delete, delete. Who's got the delete? Who's got the delete key? So delete that. Delete that. delete that. And I can begin again. All right. P. Assign the P's. P there. P there. Assign the Q's. And now I do the negations. Not true is false. Oh, what's going on? Look. Silly boy, I've got that turned on. All right, now I've got to go through my cells and make sure that's turned off. All right. So we'll do that and that. Now it's off everywhere. And let's get back to it. Sometimes this seems quicker. Sometimes it doesn't. Here we go again. So, not true is false. Not true is false. Not false is true. Not false is true. Done with that. Okay, let me do this one. Not true is false. Not false is true. Not true is false. Not false is true. And we're done with that. And then we can do this whole expression. False and false are false. False and true are false. True and false are false. True and true are true. And so I'm done with these. And I'm done with these. And now I can do this expression. True or true is true. True or false is true. False or true is true. And false or false is false. So I'm done with these. And I'm done with these. And now I can calculate the truth value that comes out under the major operator. True, if and only if false, is false. True, if and only if false, is false. True, if and only if false, is false. False, if and only if true, is false. So we're done with these. We're done with these. And here's our result. And let's look at our definition again. A contradiction is a proposition which has a form such that it is necessarily false. This means that it could not possibly be true. It's false under any possible circumstances or in any possible world. So when we analyze it under the truth table, it will always come out as false under that major operator. Now, a contingency is a proposition which has a form such that it is neither necessarily true nor necessarily false. This means that it could be true in some circumstances and false in others. When we analyze the proposition with the truth table, it will always come out as a mixture of true and false under the major operator. So if we said he is a hobbit or he is an elf, and he's not a hobbit or he's not an elf, here we've got hobbit, he's an elf with my P's and Q's, which becomes H or E, and not H or not E, which becomes P or Q, and not P or not Q. Then I've already went ahead and generated the truth table. Remember to put the spaces there. And assign the truth values under the P's and Q's. And then first you do the tildes, first you do the negations, and now I'm ready to do the whole expressions, right? Sub-expressions. True or true is true. True or false is true. False or true is true. False or true is true. Oh, look, I made the same mistake again. What the heck? My friends, see how you have to pay attention? Even I, Herr Professor Getch, can make mistakes. So just like it says in this Berenstein Bears book I read to my granddaughter Junie, let this be a lesson to you. This is what you should not do whenever Father Bear made a mistake, right? Well, I've now corrected my mistake. Always remember in the first one, true, false, and then true, true, false, false. You alternate, then you double, right? And I've went ahead and assigned the truth values again and calculated out the negations, so we're ready to go. All right. False or false is false. False or true is true. True or false is true. And true or true is true. So we're done with these guys. Or gals, I suppose. There we go. Or whoever they want to be. There we go. And now we can calculate this one. True or true is true. True or false is true. False or true is true. And false or false is false. And I'm done with them. And I'm done with them. So now I can calculate the major operator. True and false is false. True and true is true. True and true is true. And false and true is false. So as you can see, we have a mixture. Oh, we're done with those, so let's mark them out. Just for completeness' sake. We have a mixture of trues and falses under the major operator, so it's a contingency. These statements are equivalent is to join them as a biconditional, because if you do, they'll form a tautology. So here's our two statements we were comparing earlier, and we join them with a biconditional. So then we turn this into a truth table. By converting text to table. And we have tab, 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 4 possible worlds. Then create our guide column, assign our truth values, do the negations if there are any, and calculate the values of the expressions. True then true is true. True then false is false. True, true. Done with them. Done with them. That gives us these guys left. So let's do this one now. False or true is true. False or false is false. True or true is true. And true or false is true. And so we're done with them and them. At this point, we can go true if and only if true is true. False if and only if false is true. True if and only if true is true. And true if and only if true is true. So we know the expressions are equivalent because we've joined them as a biconditional and they formed a tautology. Now, logically contradictory propositions are propositions which have a form such that they will always have the opposite truth value under the same circumstances or in the same possible worlds. And when we analyze them, the truth values will be the opposite of each other. So here we have our two expressions. If he's a Jedi, then he's force sensitive. If P, then Q. He's a Jedi and he's not force sensitive. P and not Q. We've generated our guide column. We've assigned our truth values and done the negation, and now we're ready to calculate. True then true is true. True then false is false. False then true is true. False then false is true. We're done with them. We're done with them. Here's our result. We go over here. True and false is false. True and true is true. False and false is false. False and true is false. Done with them. Done with them. here's a result. And as you can see, where this is true, this is false, where this is false, this is true, and so on. Since they're not logically equivalent, then if we join them as a biconditional, they will form a contradiction. So, I've done my guide column. I've assigned the truth values, done the negations. True then true is true, true then false is false, false then true is true, false then false is true. So I'm done with them. And I'm done with these guys. We go over here. True and false is false. True and true is true. False and false is false. False and true is false. So, I'm done with them. I'm done with them. And now I can calculate the major operator. True if and only if false is false. False if and only true is false. True if and only if false is false. True if and only if false is false. And we see we've generated a contradiction by putting it in the form of a tautology, so they're not logically equivalent. Now hang in there, brothers and sisters. We got one more thing to learn, and we'll be through with this for this lecture. Logically consistent propositions are propositions which have a form such that it's possible for them all to be true under the same circumstances. When we analyze the set of propositions with truth tables, there will be at least be one line or possible world in each truth table where they all come out true under the major operator. Now, we could be comparing two statements to see if they're consistent. 3, 4, 5, 6, 7, 8, 9, 10. It wouldn't matter. It'd just be a set of statements. And here are the three we're comparing. He's a Jedi or he is force sensitive. He's a Jedi and he is force sensitive. And either he's not a Jedi or he is force sensitive. And there's our universal form. Is this a consistent set of statements? Right? Well, here, since we're comparing three, I'm dividing them like I did with the two into three separate sections so we don't get confused. So this is A, this is B, and this is C. So remember how that works. We highlight, insert, table, convert text to table. We still have only, thank God, 4 possible worlds. So we do tab, 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 tab. We have our 4 possible worlds. And now I can divide up my statements by putting in the grayscale there and there so that I don't get confused. That's what's going on here. It's just a way of keeping me from getting confused. Sort of a bookkeeping method. Right, so there's A, there's B, there's C. So I make my guide columns, assign my truth values, do the negations, and I'm ready to calculate. True or true is true. True or false is true. False or true is true. False or false is false. Done with these guys. Done with these guys. There's my result. Then I go on to B. True and true is true. True and false is false. False and true is false. False and false is false. Done with them. Done with them. Here's my result. Over here. False or true is true. False or false is false. True or true is true. True or false is true. Done with them. Done with them. There's my result. Now, is there a line where I have all truths? Well, not there in world 4, not there in world 3, not there in world 2, but in world 1 I do, right? True, true, true. So it's possible, right? It's possible in world 1, right there, for it all to be true at the same time, which is all our definition says. Right? That there should be at least one instance where we can find them all true in that way. Similarly, if a set of statements is inconsistent, right, a set of propositions, when we analyze it, there will not be any lines where all come out true under the major operator. In other words, we've got true, false, so those can't all be true. We've got false, true, no, false, false, no, true, false, no. There's no line where there's a true there, and a true there. So they're logically inconsistent. And finally, a little fun with truth tables. Of course, we've been having fun all along, but consider this statement. Bilbo will have a second breakfast and smoke a pipe unless he's lost in the wilds or he's trying to burgle Smaug's lair. So if we give our dictionary H-S-L-T, P-Q-R-S, right? We translate it. H and S are L and T. P and Q are R and S gives us 2 to the 4th power. 1, 2, 3, 4. 16 possible worlds. So how do you do 16 possible worlds? Well, first you make your guide column. P, Q, R, S. And then we have P and Q are R and S. And we're going to do that. And we're going to insert table. Convert text to table. Okay. And then we've got to go 16 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now notice what we do here. We go to the far right guide column and we alternate trues and falses. So true, false, true, false, true, false, whoop, false, true. All right, but you got to be careful. If you're getting tired like me, you might start making mistakes. So we have true, false, 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 true, false. In the next column over, you double it. True, true, false, false, true, true, false, false, true, true, false, false, whoop, false, false, true, true, false, false. And the next column over, you double it again. True, 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 false, 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 true, 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 false, 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 whoop, false. And in this last column, you double it again, or essentially divide it in half. True, 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 true. False, 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 false. Now you want to do it exactly like this for several reasons. One is, it's an algorithm. If you follow it exactly like I say, you can't go wrong unless you fall asleep at the wheel like you've seen me do a few times. Secondly, it'll make it easier for me to grade. So if you started over here and doubled it and then did it some other way, it's going to make it confusing as hell when I try to check your answers on an exam. And you don't want to confuse me when I'm checking your answers on an exam. But anyway, this first column alternates. The last one divides it in half, and you double, and then you double again. Now this is where it comes a hell of a lot easier on a word processor, because if you're doing it by hand, you then go to each one and go like, true, 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 writing it in. But here, using the handy-dandy work of, in fact, truth tables inside our computers, enabling us to do truth tables. That's kind of funny, right? So we got a P. Now we want to do the Q. So we just copy that, click on that, overwrite cells, then we have R. Copy that. Then we have S. And we copy that. And then, just because it looks cool, we can go ahead and do that. And we highlight our major operator here. And we're ready to start calculating, right? You'd go true and true is true, true and true is true, true and true is true, true and true. Actually, you could go real fast here because true and true, if there's a false, the whole thing will be false. But in any case, you'd calculate this, the and, then you'd calculate the or, then you'd calculate that, and see what results, right? I wonder what it is. Well, it turns out, if you calculate everything out, you'll see there's a mixture of trues and falses under the major operator. And this means this is a contingency, or a contingent statement. It may be true or it may be false, depending on which possible world you find yourself in. So this is what Ludwig Wittgenstein was thinking about when he was in the trenches in World War I under an artillery barrage, wondering if he was going to die. He began to think about possible worlds and how logic and truth go together. And he scribbled it down in a notebook, which became a text that influenced Bertrand Russell and other logicians, and eventually resulted in you and I learning how to do what he thought of doing while he was at risk for his life in World War I. Such is the strangeness and wonder of the world we're in, as we learn to study logic to think about the strange and wonderful world we're in. Thank you for your very kind attention.